Dear students, today I am going to discuss topic named solid state. So, in which useful and important topic for JEE Advanced determination of coordination number and neighboring atoms. So, what is meant by coordination number? So, coordination number is nothing but, say for example, this is a particular atom A. So, this atom is surrounded by some number of atoms. These atoms directly in contact with this particular atom. This number is known as coordination number. And here for this atom there are 6 atoms. So coordination number for this central atom is 6. Now these numbers are also known as directly in contact with the central atom, or A is nearest atom. These are known as nearest atoms. Similarly, I can draw one more layer. Again, these are also known as neighboring atoms, but not known as coordination number. So the second layer, next neighbor, you can say next neighbor. Next one more layer, can say next two, and the next 3, and so on. So coordination number is nothing but the atoms which are directly in contact with the central atom is known as coordination number. Remaining atoms simply known as neighboring atoms and not known as coordination number. Right. Now, to understand this concept of coordination number, just consider a building, isolated building, I can say isolated building, having 4 rooms in the ground floor and 4 rooms in the first floor. This is the ground floor and this is first floor. So a person is residing in one room in the ground state. Would like to find out how many neighbors this person has. Now, just imagine to find out the number of neighbors for this person, particular person. Just imagine this is a point where in the ground floor shared with 4 other rooms, and hence contribution for each room is 1 by 4. So on this is the ground floor. So on the top of this I am constructing first floor. Again I can keep all the 4 rooms on the top. So total this atom is common to 4 in the below and 4 in the above. I can place these 4 rooms on the top. Now their contribution is 1 by 8. So this is a point is common to all 8 rooms and contribution to each one is 1 by 8. Similarly, I am taking this is a point where initially this is a common to 2 rooms. Now I can place these 4 on the top. So contribution now 4 shared with the 4. So contribution is 1 by 4. Similarly, if atom is present here, then this is belongs to both the rooms and hence contribution is 1 by 2. Then if it is present here, again shared with the contribution is 1 by 2, and so on. You can find out. Then if it is in the middle, if atom is in the middle, it belongs to only that atom. That atom is belongs to only that one room, and hence contribution is 1. Entirely belongs to that unit cell or nothing but in that room only. So this is about. Now to explain properly, this is a 2-dimensional representation. To explain 3-dimensional representation, I can consider this is a room as 1 unit cell. So I can consider room as 1 unit cell. Now this is a unit cell. Now this is a unit cell. Now in this unit cell, atoms I can keep, these are known as corners. I can keep atoms corners at corners. So there are 8 corners in the cube. Now this is known as face center. I can keep atoms on the face center. We have 6 phases. How many phases we have? 6 phases. So center of the face is known as face center. This is one face pointing towards you, center of the face. Now this is a face, back side, right side. Now this is the center of the phase. So we have 6 atoms on the phase centers. Similarly, in the body center, I can keep 1. So these are known as lattice points, position of atoms in the cubic cell. Now, this is a basic representation for any cubic lattice, simple cubic lattice, body centered cubic lattice, or phase centered cubic lattice. This is a basic unit for simple cubic lattice, body centered FCC. Now, simple cubic lattice structure is nothing but atoms located only at corners, and no on phase centers, and no atom on body center. Body centered cubic lattice is nothing but atoms located in the body center and as well as corner. So corner plus body center, and here only at corners, and here corner plus face centers. So together gives rise to structure of the corresponding crystal lattices. Okay, right. Now we would like to find out contributions first of all. Just this is a point where I was taken, this is a point now here. So 4 rooms on the below and 4 rooms on the top. So contribution to each unit cell is nothing but 1 by 8. So contribution to each room is 1 by 8. Next, come to this point. Now this is a 4 atom, so shared with 4 other rooms, so 1 by 4. Again, similarly, this is also 1 by 4. Right? Again, this is also 1 by 4. Now, if an atom is present on the face, then this is belongs to another one. Now sharing other unit cell. Now this is off. Now this is no more. Now total we have 4 rooms. Just consider this is 1 unit cell or 1 room. Now again draw 1 more. So on the top I can go total 4 rooms, 3-dimensionally in 1 floor. Then on the top we have 4. So total considering, so this is atom, this is the phase, no more attached to the any other. So contribution is only 1. And here also bottom plane, bottom phase, no connected to the other room, its contribution is 1. Now this is the room, here 1 more room you have. Here 1 and here 1, here 1. So this is a atom or any point, if it is existing over here, shared with 1 more room, and hence contribution is 1 by 2. Again, this is a room, contribution, this is a point, contribution to half. So this is a point, corner 1 by 8, shared with 8 other unit cells. Just imagine corner of it. Next 1 by 4. This is half, again sharing with 2. Now this is the bottom, we have last one, so no sharing with any other, just a corner of the building. So these are the put again, this is an atom sharing with 2 other. So this is about contribution of the corresponding atoms, 3-dimensional representation. So from these contributions, I can find out coordination numbers and neighboring atoms for simple cube, BCC and FCC. Stop. So FCC, corners and face center atoms. Now would like to find out contributions to each. So as early I said, these are the 4 atoms, 4 rooms in the first floor, 4 rooms in the ground floor. I said the building was isolated one, only 8 rooms. No other attachments to that building. Considering only 8 rooms, I can find out the contributions. Not considering attachments of the total. Only I am considering 8 rooms. So to find out contribution, I am considering only 8 rooms. So this is an atom, nothing but shared with 8 other rooms. So contribution to each one is 1 by 8. This is a point. Next. This is a point where 4 shared with 4 other unit cells, 1 by 4. So directly come to the bottom, shared by 2 other, so contribution is 1 by 2. Directly come to this, then shared with other 1 by 4. Then this is again, this is a shared with 4. Just imagine, so 4 rows and single building, no attachments. So this is the atom come here. This is an atom. I can place. So come to 4 other rooms 1 by 4. Now contribution to 1. So 1 by 4. Now this is common to 2. This is half. Again, this is a common to 2. This is half. Contribution 1 by 2. Right? Then how much it is? This is corner at the bottom. Contribution belongs to only 1 unit cell, corner of the building. So now 1. No sharing in what? 1. Next. Face center atom I am taking. Face center atom, this is the lower bottom floor. No sharing with any other room. So its contribution 1. Again, this is the wall, end, no other. End room, no other room after this. So we have 1 room here, we have 2nd room here, we have 3rd room here. So 4 rooms. Now this is the wall common to belongs to only that unit cell. So contribution is 1. Next, this is the body center. Then body center means that atom belongs to only middle. So contribution 1. Again, this is a face. This is an atom. This is a wall common to other room, and hence contribution is 1 by 2. Again, this is a wall common to 1 more room here. Now contribution 1 by 2. Now this is a face, back side. This is a face, wall, then this is common to 1 more, and here also you have 1 by 2. Face center. Then pointing towards you. Only 1, no other room or here. So this is about contribution of atoms which are located at different lattice points. Now, based on this, I can find out coordination number and neighboring atoms. Now, this is a very important now. So, first of all, I am taking simple cubic lattice. In simple cubic lattice, imagine thinking only 8 rooms, isolated, not 3-dimensional, not only consider 4 rooms. Okay? In simple cube, in body center, in face center, would like to find out coordination number, neighboring atoms. So first of all, I am taking simple cube. So as you know, simple cube is nothing but atoms present at corners. Only at corners. Atoms present only at corners. So I can draw now simple cube. Now only corners, you have 8 corners. So total 8 corners here. Now this is a simple cube representation. Now we would like to find out coordination number and neighboring atoms. Now to consider coordination number and neighboring atoms, I am taking one atom is a reference atom. With respect to the reference atom, I can find out coordination number of other things. So as I said, you have only 8 unit cells in the system. Okay, so I am taking out now, this is a simple cube. Now this is a reference atom I am taking over here. Now to this reference atom, this is an atom separated with the distance A. This is known as H length, and this is an atom separated with the distance root 2A, since it is phase diagonal. Now separated with the distance. Now this is an atom separated with the distance. Now this is known as body diagonal root 3A. To this atom, this is an atom separated with the distance A. This is an atom separated with the distance root 2A. This is an atom separated with the distance root 3A. This is a body diagonal, this is a phase diagonal, this is edge length. So this is, I am writing this is as atom 1, this is as atom 2, and this is as atom 3. Okay, so I'm marking now atom 1, atom 2, atom 3. To this reference point, distance is A, and to this we have root 2A, and here root 3A, and this is nothing but 1 into A, I can write. This is 1.4 times A, this is 1.7 times A. So to this point, this atom is very near. I can say this is the nearest atom. This is the nearest atom. Now this is separated, next to nearest atom, and this is the next to nearest atom. I can say next to next one, nearest atom. Since this is an atom nearer to this reference point, directly in contact with this atom is directly in contact with this, and hence this is known as coordination number. From this I can find out the coordination number. So from the nearest atoms, you can find out the coordination number of this atom with respect to the reference. Now this is about the distances of nearest, next one, and next one. Right. Now can find out coordination numbers. For coordination number for this or neighboring atoms for this. Only for first one can say coordination number for neighboring atoms. For the rest only neighboring atoms. Then how to find out neighboring atoms? Simple. Again can take the simple cube. This is a simple cube. Now in this simple cube, this is the reference point as usual. Now this is the nearest atom separated with the distance A. This is also nearest atom separated with the distance A. This is also nearest atom separated with the distance A. So all the three atoms separated with the same distance. So if atom is present here, its contribution is 1/4 as earlier was discussed. So total number of atoms with equal distance. How many atoms are there in this cube? 3 atoms, same distance. Then contribution to each one is 1/4. So like this is a one room or one unit cell. This is shared with 8 more unit cells. So I can write for one unit cell 3. Like this we have 8. So 8 into 3. This is nothing but 6. So number of neighbors. Number of neighbors for this atom. Number of neighbors for this one. Number of neighbors for this atom. This is the nearest one. This is next. This is the next two. So number of neighbors for this is 6. So I can write 6. That 6 is here. It is known as coordination number. Similarly, for this atom I can find out. So I can draw the, again we can consider simple cube. Now this is a simple cube. Now this is the reference point. Now this is an atom. Nothing but phase diagonal. Right? Again this is an atom. Nothing but phase diagonal. Now this is an atom. Nothing but phase diagonal. Here if it is there, contribution is 1/2. Here if it is there, contribution is 1/2. Now this is one phase diagonal. This is another phase diagonal. Then one more you have phase diagonal back side. So you have one more. So again total 3 atoms. So here also contribution is 1/2. Contribution 1/2. So total we have 3 atoms. So 3 atoms, contribution is half. Then this is this is one unit cell. Then we have 8 unit cells into 8. Then total 12. So for the next atom, neighboring atoms are 12. Next 2 atoms. I'm taking next 2 atoms. next to 2 atom. Again, this is the reference. This is nothing but body diagonal. This is nothing but body diagonal. Only one atom you have. So 8 into here. If atom is present here, contribution is 1. So 8 into. So total next to 3, next to 2, neighboring atoms 8. So I can say in the simple cube 6, 12, 8. So neighbors for next 2 is 12, next one is 12, next 2 is 8. Now this is the nearest. Now this number is known as coordination. So this is how you can find out coordination numbers, neighboring atoms in simple cube. So in the examination, you may get the questions, distance between next one, next two and nearest. I will learn the distances. At the same time, coordination number, nothing but neighboring atoms. So this is an atom is surrounded with 12 other atoms. Now this is an atom surrounded with 8 other atoms. So now coordination number, this is an atom surrounded with 8. So coordination number, these two are tagged in content. Similarly, can go for FCC. FCC. So FCC is nothing but atoms, phase centers and corners. Atoms, phase center and corners. These are the corner atoms. Then phase center atoms I can mark. We have 6 phases. Now this is FCC structure. Again, we would like to find out coordination numbers and neighboring atoms. Again, I am taking out separately. Again, with respect to the reference, now this is an atom is reference. Now this is an atom is separated with, this is an atom is separated with distance A. This is an atom is separated with phase center. This is a phase center atom, then separated with the distance. Total distance is root 2a. Half of the distance root 2a by 2. This is nothing but a by root. So here it is a by root 2. Now this is an atom separated with the distance. Now this is an atom separated with the distance root 2a. Next, this is an atom separated with the distance body diagonal root 3a. At the same time, adjacent, this is a corner atom. To this corner atom, adjacent phase centers. This is one adjacent phase center. Now to this adjacent phase center, the distance between these two, root 3 by 2 times a. So I can say this is an atom separated with the distance a. This is an atom separated with the distance a root 2. This is root 2a. This is root 3a. This is root 3 by 2a. This is nothing but adjacent phase centers. Adjacent phase centers. Now, distances you can find out. The smallest distance is a by root 2. Next, a. Next, root 3 by 2a. Now this is a by root 2. Just to multiply with root 2a. Right? This is a by root 2. Next, a. Next, root 3 by 2a. This is separated with the minimum distance. I can say this is the nearest one. Now this is the next one. Now this is the next two. And so on you have. So a by root 2, a, root 3 by 2, a. So this is the nearest one. So I am marking over here. This is next to nearest one. Next. This is next to nearest. This is next one, next. I was given, next one I was given, next two I was given. Suppose if you want to find out the next three, generally up to two they will ask in the examination. But if you want, you can simple trick. Now this is multiplied with the root 2, you will get this. This is multiplied with the root 3, you will get this. This is multiplied with root 4. So root 4 a by root 4. Then next multiply with root 5 a by root 4. Then a simple trick to find next 3, next 4. So now coordination numbers required or neighboring atoms required for this. So I am taking all these things now again first. For this atom I am going now nearest atom. First nearest atom I am going. Now this is a reference point. Now to this reference point, nearest atom is, this is nothing but nearest atom. This is a body diagonal. This is a phase diagonal. So in the phase diagonal we have atom A here. Again here also can find one more. This is also, and here also find one more phase diagonal. This is one phase, this is the second phase, and this is the third phase. So total 3 atoms. Contribution to each one is half. What is the contribution here? Half. Then like this, we have 8 other unit cells. Now this is shared with 8 other unit cells. So total is how much now? 4. So now for the nearest atom, coordination number, this is nothing but 12. Now this 12 is nothing but coordination number here. Similarly, next atom I can find out as I repeat. Now this is reference atom. This is A. Again this is A. This is also A. Again contribution here 1 by 4. So how much contribution here? 1 by 4. Total 1 by 4. 3 atoms into 8. Now this is nothing but 6. So neighboring atoms for this next one is 6. Now adjacent. For this I am going now next. So in the unit cell, in the FCC unit cell, this is FCC unit cell. Again reference. There are 3 adjacent. This is a corner. This is adjacent one atom. Right? Next, this is a corner. This is a face adjacent. Now towards this is a face adjacent. Now one more we have there. Then face adjacent. So total 3 face adjacents. Contribution is 1 1 1. So total now I can find. This is shared with 8. So 8 into 1 2 3. So total how much now? 24. So here it is 24. Here it is 24. So neighboring atoms for this point is 24. So 12 6 24. In 12 6 24, this is known as coordination. So this is an atom. This is an atom directly in contact with the reference atom. So coordination number this point is 12 6 24. So this is about FCC coordination number of neighboring atoms.